Hello and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind, to step away from screens and deadlines and the relentless rush of now, and step quietly into the vast starlit corridors of our own galaxy, where time stretches back not thousands of years but billions, where the story isn't written in distant places but right here, in the spiral arms of the Milky Way, the galaxy we call home. Here, in this space between present and primordial, we wander together through the band of light that has arched above humanity since the first eyes looked upward. We peer through centuries of wonder at the pale river stretching across darkness, the ghostly glow that ancient peoples called the Path of Spirits, the backbone of night, the Silver River. We stand alongside the astronomers who first turned telescopes toward that hazy band, and discovered it was not mist at all, but countless stars, more suns than anyone had imagined, each one a furnace of fusion, each one a world unto itself. Each episode here isn't just about telescopes and measurements. It's not about memorizing distances or cataloguing stellar types. It's about the human desire to understand where we belong, the scientists dedicating lifetimes to mapping a galaxy from the inside, the photographs capturing structures we can never step outside to see. It's about one of the most intimate frontiers humanity has ever explored, where we discover that every atom in our bodies was forged in stars, where the galaxy isn't just our address but our origin, and where everything we are is woven into the fabric of this immense spiral system. If you enjoy these quiet journeys through our cosmic home, a like and subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. The Milky Way has been with us since long before we knew its true nature. On any clear night far from city lights you can see it, a faint band of light stretching from one horizon to the other, crossing the darkness like a river spilled across the heavens. It has been there for every generation, every civilization, every person who has ever looked up and wondered. The ancient Greeks saw it as milk from the goddess Hera, scattered across the sky. The Chinese called it the Silver River, a celestial waterway separating lovers. Indigenous peoples saw it as the backbone of night, the path of birds, the road of spirits travelling between worlds. Every culture that gazed upward found something in that pale glow, something worth naming, worth weaving into their stories. For thousands of years no one knew what it truly was. Without telescopes, without the tools of modern science, the Milky Way remained a mystery wrapped in mythology. It looked like mist, like fog, like smoke drifting through the darkness. Some believed it was an opening in the celestial sphere, a crack through which divine light leaked into our world. Others thought it was the remains of a great fire, ashes scattered by gods or spirits. The explanations varied across continents and centuries, but the wonder remained constant. That band of light was too prominent to ignore, too strange to dismiss. It demanded explanation, even when explanation seemed impossible. The setting for our story is not a single place, but everywhere under open sky. From the deserts of Arabia to the plains of North America, from the mountains of Tibet to the beaches of Polynesia, the Milky Way has stretched overhead, unchanging in its presence, even as civilizations rose and fell beneath it. It was there when the pyramids were built, when Rome conquered Europe, when the first humans crossed into the Americas. It witnessed the birth of agriculture, the invention of writing, the development of mathematics and philosophy. Every major event in human history unfolded under its glow, though few understood what they were seeing. The Milky Way is visible from every point on Earth at some time of year, though its appearance changes with the seasons. In summer, for those in the northern hemisphere, the brightest part arcs across the southern sky, rich with detail crossed by dark lanes of dust. In winter, a fainter section appears overhead, less dramatic but still present. The band circles the entire sky, a feature so large it requires the whole night to take in fully. Ancient astronomers noticed this, tracking its path, measuring its position relative to the horizon, using it as a calendar and compass. They did not know they were mapping a galaxy from the inside, but they were laying the groundwork for what would come. By the time humans began to ask systematic questions about the heavens, the Milky Way had already been observed for thousands of years, yet it remained unexplained. Was it close or distant? Was it part of Earth's atmosphere or something beyond? Was it solid, liquid, gaseous, or perhaps something else entirely? The questions accumulated without answers. The tools did not yet exist to pierce the mystery. All anyone could do was look, wonder, and speculate. This was the setting when Galileo Galilei, in 1610, turned a newly invented telescope toward the heavens. He was not the first to wonder about the Milky Way, but he would be the first to see it for what it truly was. That moment, when the hazy band resolved into individual stars, would mark the beginning of a transformation in human understanding. We were about to discover that we live inside something far larger, far stranger, and far more beautiful than anyone had imagined. The Milky Way was not a river of milk or a path of spirits. It was a galaxy, and it was our home. In 1610, Galileo Galilei aimed his telescope at the Milky Way and saw something that would change everything. The pale band that had puzzled humanity for millennia suddenly resolved into countless individual points of light. Where there had been mist, there were now stars. Where there had been a vague glow, there was now a multitude so vast that Galileo could not begin to count them. He described what he saw with wonder bordering on disbelief. The Milky Way, he wrote, was nothing but a congeries of innumerable stars grouped together in clusters. Upon whatever part of it the telescope is directed, a vast crowd of stars is immediately presented to view. Many of them are rather large and quite bright, while the number of smaller ones is quite beyond calculation. This was not what anyone had expected. The prevailing belief was that the Milky Way might be a cloud, perhaps atmospheric, perhaps celestial, but certainly not a collection of discrete stars. Galileo's observation shattered that assumption. The telescope, barely more powerful than modern binoculars, was enough to reveal a truth hidden from the naked eye for all of human history. The Milky Way was not a single mysterious entity, but a gathering of stars so numerous and so distant that they blended together into a uniform glow. Each tiny point of light in Galileo's telescope was a sun, perhaps like ours, perhaps with worlds of its own. The implications were staggering. The discovery sent ripples through the scientific community, though it took time for the full significance to be understood. Galileo had proven that the universe contained far more stars than anyone had realized. If the Milky Way alone held countless suns, then the night sky was filled with possibilities beyond previous comprehension. This was not simply an academic revelation. It touched on fundamental questions about existence, about humanity's place in the cosmos, about the nature of creation itself. If there were so many stars, might there be other worlds? Might there be other beings looking up at their own night skies asking the same questions? But Galileo's discovery also raised new mysteries. If the Milky Way was made of stars, why did it appear as a band? Why did it stretch across the sky in a particular pattern? Why were some regions brighter than others? And most puzzling of all, if we could see so many stars in the Milky Way, where were we in relation to them? Were we inside it? Outside it? At its centre? At its edge? The telescope had answered one question, but opened a dozen more. The Milky Way was no longer a simple mystery to be explained away with mythology. It was a complex structure demanding systematic investigation. Over the following centuries, astronomers built better telescopes and observed the Milky Way with increasing detail. They noticed that it formed a complete circle around the Earth, visible as a band because we were seeing it edge on. They noticed that it was thicker in some directions, suggesting a concentration of stars toward what might be a centre. They noticed dark patches where stars seemed absent, though they could not yet explain what caused those gaps. Each observation added to the picture, but the picture remained incomplete. The Milky Way was clearly important, clearly vast, but its true nature remained elusive. By the 18th century, astronomers like William Herschel began trying to map the Milky Way by counting stars in different directions. Herschel spent years cataloguing thousands of stars, trying to determine the shape and extent of what he called the sidereal system. His conclusion was that the Milky Way was a flattened disk of stars with the sun near its centre. This was a reasonable interpretation based on the evidence available, but it would later prove to be incomplete. Herschel could not account for the dust that obscured distant stars, making some regions appear less populated than they truly were. He was mapping the visible galaxy, but the visible galaxy was only a fraction of the whole. The discovery that the Milky Way was made of stars was the spark that ignited modern astronomy. It transformed a mythological question into a scientific one. It shifted the focus from asking what the Milky Way represented to asking what it actually was, and it established a pattern that would repeat throughout the history of astronomy, the application of new technology revealing truths that forced humanity to reconsider its place in the universe. Galileo's telescope showed us that the Milky Way was not a simple phenomenon, but a complex system, one that would take centuries to understand fully. And in showing us that, it showed us that we lived in a universe far larger and more intricate than we had ever imagined. The discovery was not immediate in its impact. It took generations for the full weight of Galileo's observation to be appreciated. But looking back, we can see that moment in 1610 as a turning point. Before the telescope, the Milky Way was a mystery explained by stories. After the telescope, it became a challenge explained by evidence. The shift from mythology to astronomy had begun, and with it came the slow, careful process of discovering that we were not observers of the Milky Way from some distant vantage point. We were participants, living inside it, part of the very structure we were trying to understand. The response to Galileo's discovery was not uniform. Some embraced it with excitement, seeing in those countless stars a confirmation of the universe's vastness and complexity. Others met it with skepticism, questioning whether the telescope truly revealed reality or merely created illusions in glass and metal. The debate reflected a deeper tension in how humans process revelations that challenge their understanding of the world. When confronted with evidence that the Milky Way contained more stars than could be counted, that the pale band overhead was not a singular phenomenon but a gathering of distant suns, reactions ranged from wonder to resistance. Among astronomers and natural philosophers, the discovery inspired a mixture of awe and intellectual curiosity. If the Milky Way held so many stars, what did that mean for the structure of the heavens? The prevailing cosmology placed Earth at the centre of a relatively small universe, bounded by the sphere of fixed stars. Galileo's observation suggested something far more expansive. The stars were not all at the same distance from Earth. They were scattered across vast reaches of space, some closer, some farther, arranged in a pattern we could only glimpse from our particular vantage point. This realization was both thrilling and disorienting. The universe was larger than anyone had imagined, and humanity's position within it suddenly seemed less certain. Religious authorities had mixed reactions. Some saw in the multitude of stars evidence of divine creation on a scale befitting an infinite creator. If God had made countless suns, then surely that demonstrated his power and glory beyond previous understanding. Others worried that such a view diminished Earth's importance, undermining doctrines that placed humanity at the centre of God's plan. The telescope, in revealing so many stars, seemed to scatter humanity's significance across an impossibly large canvas. These theological concerns would persist for generations, shaping how the Milky Way's true nature was discussed and taught. For ordinary people, those without access to telescopes or astronomical training, the discovery remained abstract. The Milky Way still looked the same to the naked eye. It was still the pale band their ancestors had seen, still the subject of familiar stories and myths. The idea that it was made of stars did not immediately change their experience of the night sky. But slowly, as knowledge spread through books and lectures, as telescopes became more common, the realization began to permeate broader culture. The heavens were not what they had seemed. The universe was deeper, fuller, more crowded with light than anyone had suspected. Some astronomers expressed disbelief at the sheer number of stars Galileo reported. Could there really be so many? Were they truly separate suns? Or might they be some other phenomenon? Perhaps luminous clouds that only appeared star-like through the imperfect lenses of early telescopes. These doubts were not entirely unreasonable. The instruments of the time were crude by modern standards, prone to aberrations and distortions. It took repeated observations by multiple astronomers using different telescopes to confirm that Galileo was right. The Milky Way truly was a multitude, and the multitude was real. The discovery also inspired artists and poets, who began to incorporate the new understanding into their work. The Milky Way became a symbol not just of mystery, but of infinity, of countless worlds beyond our own. Writers imagined other Earths circling other suns, other civilizations gazing up at their own versions of the Milky Way. This imaginative leap from observing stars to envisioning other worlds was one of the first responses to Galileo's revelation. If there were so many stars, the reasoning went, then surely we were not alone. The universe must be teeming with possibility. Yet alongside the awe and speculation came a quieter, more personal response: humility. To look at the Milky Way and realise it contained more stars than one could count in a lifetime was to confront the limits of human scale. Each of those stars was a sun, burning with the same nuclear fires that powered our own. Each was separated from the others by distances so vast that light itself took years to cross them. And all of this existed whether humanity observed it or not, whether we understood it or not. The Milky Way had been there long before the first human eyes opened, and it would remain long after the last closed. This awareness did not diminish wonder, but deepened it, adding to the sense that we were part of something far greater than ourselves. Some responded to the discovery with fear, though they rarely voiced it openly. If the universe was so large, if the Milky Way alone held countless stars, then what did that mean for humanity's significance? Were we merely one planet among many, one species in a cosmos that barely noticed us? This existential anxiety would resurface repeatedly over the following centuries, as each new discovery pushed humanity further from the centre of creation. But in the early 1600s, it was still nascent, a faint unease overshadowed by the excitement of discovery. The first responses to the revelation of the Milky Way's true nature set patterns that would persist throughout the history of astronomy. There was always a tension between acceptance and resistance, between those who embraced new knowledge and those who clung to familiar explanations. There was always the interplay of science, religion, art and philosophy, each trying to make sense of what the evidence revealed. And there was always the dual experience of feeling smaller in scale yet richer in understanding, humbled by the universe's vastness yet elevated by the ability to comprehend it. The Milky Way, in being revealed as a galaxy of stars, became a mirror reflecting humanity's relationship with the cosmos. Our wonder and our doubt, our curiosity and our fear, all bound together in the pale band of light stretching overhead. The more astronomers learned about the Milky Way, the more they encountered a fundamental contradiction. They could see it, measure it, map its brightest regions and darkest lanes, yet they could not step outside it. Every observation was made from within the very structure they were trying to understand. It was like trying to describe a forest while standing in the middle of it, surrounded by trees, unable to climb high enough to see the whole. The Milky Way presented itself as both observable and obscure, knowable and mysterious, a subject of scientific inquiry that resisted complete understanding precisely because of where we stood. This contradiction shaped every attempt to map the galaxy. When William Herschel counted stars to determine the Milky Way's shape, he assumed that he could see equally far in all directions. If one region of sky appeared to have fewer stars, he reasoned, it must actually contain fewer stars. But this assumption ignored the presence of dust, vast clouds of fine particles that absorbed and scattered light, hiding entire populations of stars from view. Herschel was mapping the visible galaxy, but the visible galaxy was not the whole galaxy. His maps were accurate as far as they went, but they went only as far as light could reach his telescope. Beyond that, the structure remained hidden. The contradiction deepened when astronomers tried to determine where the sun sat within the Milky Way. If we were at the centre, the band of light should appear equally bright in all directions. If we were offset, one side should appear brighter, denser with stars. Observation suggested the sun was near the centre, but this conclusion seemed almost too convenient. Were we really at the heart of the galaxy, or was something else at play? The answer would not come until the early 20th century, when Harlow Shapley studied globular clusters and realised their distribution was centred not on the sun, but on a point thousands of light years away. The sun, and with it, Earth and humanity, was not central but peripheral, located in one of the outer regions of the galactic disk. This realisation was both liberating and disorienting. It solved the mystery of our position, but introduced new questions. If we were not at the centre, what was? What existed in that distant core we could barely see through the dust? And if our view was so limited, how much of the galaxy remained unknown? the contradiction persisted. We lived in the Milky Way. We were made of its matter. We orbited within its structure, yet we could not see it whole. Every map, every model, every theory was built on incomplete information, inferences drawn from fragments. Science thrives on evidence, on observation and measurement, on turning the universe into something quantifiable and understandable. But the Milky Way resisted this process in subtle ways. You could count stars, measure their distances, trace their motions, but you could never step back and confirm your conclusions with a single comprehensive view. The galaxy remained partly mysterious, not because it was fundamentally unknowable, but because our vantage point was limited. We were inside looking out, trying to reconstruct the whole from pieces. This limitation forced astronomers to develop new methods. If they could not see the galaxy directly, they would infer its structure from other evidence. Radio astronomy allowed them to peer through dust by detecting emissions from hydrogen gas. Infrared observations revealed heat from stars hidden in clouds. Measurements of stellar motions showed how gravity shaped orbits, allowing the distribution of mass to be calculated even when that mass could not be seen. Each technique added another piece to the puzzle, another way of working around the contradiction of being inside the subject of study. Yet even with these advances, mysteries persisted. The exact shape of the spiral arms remained debated. The number of arms, their pitch, their width, all were matters of ongoing research. The structure of the central bulge, obscured by dense clouds of dust, could only be inferred. The distribution of dark matter, invisible by definition, had to be deduced from its gravitational effects. The Milky Way was knowable in principle but elusive in practice, revealing itself slowly across centuries of patient observation. The contradiction also had philosophical dimensions. If we could not see our galaxy from outside, how could we be certain our models were correct? Every image of a spiral galaxy used to represent the Milky Way was actually a different galaxy, a stand-in for what ours might look like. We assumed the Milky Way was similar, but we could not prove it directly. This gap between model and reality was a constant presence in galactic astronomy, a reminder that science often proceeds by approximation, building understanding from incomplete evidence. Some found this contradiction frustrating, a barrier to true knowledge. Others found it invigorating, a challenge that demanded creativity and persistence. The Milky Way would not reveal itself easily, so astronomers had to be clever using indirect methods, comparing observations from different wavelengths, building models and testing them against data. The process was slow, but it was progress. Each generation understood the galaxy a little better than the last, even if complete understanding remained out of reach. In the end, the contradiction between science and mystery was not a flaw, but a feature of studying the Milky Way. It kept the galaxy interesting, kept astronomers humble, kept the questions alive. We live in a galaxy we can never fully see, made of matter we can barely detect, shaped by forces we are still working to understand. That combination of familiarity and mystery, of home and unknown, defines our relationship with the Milky Way. We belong to it completely, yet it remains partly beyond us, a subject of endless inquiry, a home we are still learning to know. As evidence about the Milky Way accumulated, astronomers developed competing theories to explain what they were seeing. These theories reflected not just different interpretations of data, but different assumptions about the universe itself. Some believed the Milky Way was the entire universe, that the band of stars encircling Earth represented the full extent of creation. Others suspected it was just one system among many, perhaps an island of stars in a larger cosmic ocean. The debate between these views would shape astronomy for decades, dividing researchers into camps that argued passionately for their positions. The island universe theory had roots going back centuries. Philosophers like Immanuel Kant in the 1700s suggested that some of the faint nebulous patches visible in telescopes might be distant collections of stars, similar to our own Milky Way but far beyond it. These nebulae, Kant proposed, were separate galaxies, each containing countless suns, scattered throughout infinite space. It was a bold idea, one that expanded the universe to scales almost incomprehensible. But it remained speculative, lacking the evidence needed to convince skeptics. The opposing view held that the Milky Way was unique, the totality of the stellar universe. Nebulae, according to this theory, were not distant galaxies but clouds of gas within the Milky Way, perhaps regions where new stars were forming. This interpretation seemed to fit the observations. Some nebulae showed spiral structures, but that did not necessarily mean they were galaxies. They could be swirling clouds of gas, phenomena occurring relatively nearby rather than at vast distances. Without a way to measure distances accurately, both interpretations remained plausible. The debate intensified in the early 20th century. Improved telescopes revealed more detail in nebulae, showing structures that looked strikingly similar to what one might expect from a galaxy viewed from afar. Spiral arms, central bulges, and overall symmetry suggested organisation on a grand scale. Yet determining whether these objects were within the Milky Way or beyond it required measuring their distances, a task that proved extraordinarily difficult. The tools available were not yet precise enough to settle the question definitively. Harlow Shapley, studying globular clusters in 1918, developed a model of the Milky Way that placed the Sun far from the centre. His work suggested the galaxy was much larger than previously thought, perhaps 100,000 light-years across. If the Milky Way was that large, Shapley reasoned, then it might encompass everything. The nebulae could all be features within this enormous system. There was no need to invoke distant galaxies when a single vast Milky Way could explain the observations. Heber Curtis, Shapley's contemporary, disagreed. Curtis examined spiral nebulae and noticed features that suggested they were external to the Milky Way. He observed nova explosions in some nebulae, far fainter than novae seen in the Milky Way. If these nebulae were within our galaxy, the novae should appear brighter. The fact that they were so faint suggested the nebulae were much farther away, perhaps millions of light-years distant. Curtis argued that these were indeed island universes, separate galaxies scattered throughout space. The debate between Shapley and Curtis came to a head in 1920 during what became known as the Great Debate, a public discussion held at the Smithsonian in Washington. Each presented their case before an audience of scientists and the public. Shapley argued for a large Milky Way that encompassed all visible structures. Curtis argued for a smaller Milky Way with external galaxies beyond it. The debate did not settle the matter. Both sides presented compelling arguments, and neither had conclusive proof, but it brought the question into sharp focus, highlighting how much uncertainty still surrounded our understanding of the cosmos. The resolution came a few years later when Edwin Hubble used the Mount Wilson telescope to observe Cepheid variable stars in the Andromeda Nebula. Cepheids vary in brightness with a predictable rhythm, and that rhythm is related to their intrinsic luminosity. By measuring how bright they appeared versus how bright they should be, Hubble calculated their distance. The result was stunning. Andromeda lay nearly 1 million light-years away, far beyond the boundaries of the Milky Way. It was not a nebula within our galaxy, but a galaxy in its own right, a separate island universe just as Curtis had argued. This discovery ended the debate but also transformed it. The Milky Way was not the entire universe. It was one galaxy among countless others, each containing billions of stars, each separated by vast distances. The universe was larger than anyone had imagined, filled with galaxies stretching as far as telescopes could see. Shapley had been wrong about the Milky Way being all there was, but he had been right that the Milky Way was enormous, far larger than earlier estimates. Curtis had been right about external galaxies, though his estimate of the Milky Way's size had been too small. Both theories contained truth, and both required revision. The theories that emerged after Hubble's discovery incorporated this new understanding. The Milky Way was a spiral galaxy, one among billions, each with its own structure and history. Astronomers began comparing our galaxy to others, looking for patterns and differences. They realized that galaxies came in different shapes, spirals, ellipticals, irregulars, and that the Milky Way's spiral form placed it in a particular category. The competing theories had given way to a new consensus, one built on better evidence and more powerful tools. Yet even this consensus left questions unanswered. How had the Milky Way formed? How did it compare to other galaxies? What forces shaped its structure? The theories evolved, but the mystery remained, now framed in a universe far larger and stranger than the island universe theorists had imagined. Once astronomers understood that the Milky Way was a galaxy, a massive spiral system containing billions of stars, the true investigation could begin. This was no longer about simply observing a band of light or counting stars in different directions. It was about mapping a structure so vast that light took 100,000 years to cross it, about understanding dynamics that played out over millions of years, about uncovering the history of our cosmic home. The pursuit of this knowledge would require new instruments, new methods, and new ways of thinking about observation itself. The investigation proceeded on multiple fronts. Astronomers needed to determine the Milky Way's size, its shape, its mass, and the distribution of its components. They needed to understand how it rotated, how its stars moved, how its gas and dust were arranged. Each question demanded different techniques. Distance measurements relied on standard candles, objects with known brightness that could be used as cosmic yardsticks. Stellar motions required careful tracking of positions over years or decades. The distribution of gas required observations in radio wavelengths that could penetrate dust. Every piece of the puzzle demanded patient, systematic work. Radio astronomy, developed in the mid-20th century, proved transformative for studying the Milky Way. Neutral hydrogen, the most abundant element in the galaxy, emits radiation at a wavelength of 21 centimeters. This emission passes through dust clouds that block visible light, allowing astronomers to map regions of the galaxy that had been hidden. By observing this 21 centimeter line, researchers traced the spiral arms, revealing a pattern that matched theoretical predictions. The Milky Way truly was a spiral, with arms winding outward from a central bar, and radio observations provided the first clear view of this structure. Infrared astronomy added another dimension. Dust absorbs visible light but glows in the infrared, radiating heat. Satellites like IRAS, launched in 1983, mapped the entire sky in infrared wavelengths, revealing the distribution of dust throughout the galaxy. These observations showed star-forming regions embedded in clouds, invisible to optical telescopes but brilliantly apparent in infrared. They also revealed the crowded centre of the galaxy, where dust is so thick that visible light barely escapes. Infrared light pierced through, showing a dense bulge of stars surrounding the core. X-ray and gamma-ray observatories revealed yet another layer. These high-energy wavelengths showed the most violent processes in the galaxy, supernova remnants still glowing from ancient explosions, neutron stars spinning rapidly and emitting beams of radiation, black holes accreting matter and releasing bursts of energy. The Milky Way, seen in X-rays, looked dramatically different from the serene band of light visible to the eye. It was a place of explosive energy, of matter falling into gravitational wells, of radiation streaming across space. Each wavelength told a different story, and together they built a comprehensive picture. The Gaia mission, launched by the European Space Agency in 2013, represented one of the most ambitious investigations ever undertaken. Gaia's goal was to measure the positions, distances and motions of more than 1 billion stars with unprecedented precision. By tracking tiny shifts in stellar positions as Earth orbits the Sun, Gaia calculated distances through parallax, creating a three-dimensional map of the Milky Way. The data revealed streams of stars, remnants of smaller galaxies absorbed long ago. It showed how the disk warps and ripples, evidence of gravitational interactions with satellites. It provided the most detailed map of our galaxy ever created. Spectroscopy became another crucial tool. By splitting starlight into its component colours, astronomers could determine what elements stars contained, how fast they were moving, and even their ages. This technique revealed that the Milky Way has a chemical history, with older stars containing fewer heavy elements, and younger stars showing enrichment from generations of supernova. The galaxy had evolved chemically over billions of years, recycling matter through cycles of star formation and death. Spectroscopy made this history readable in the light of individual stars. Computer simulations complemented observations. Astronomers could not watch the Milky Way evolve in real time. Its processes unfold over timescales far longer than human lifespans. But they could model those processes mathematically. Simulations showed how spiral arms form through density waves, how gas clouds collapse into stars, how galaxies merge and reshape each other. These models, tested against observations, helped astronomers understand not just what the Milky Way is, but how it came to be. The investigation became a dialogue between observation and theory, each informing the other. Ground-based surveys scanned the sky systematically, cataloguing millions of objects. The Sloan Digital Sky Survey mapped a quarter of the sky in multiple wavelengths, creating a database astronomers could query for specific types of stars, clusters, or nebulae. Surveys like 2MASS focused on infrared wavelengths, revealing cool stars and brown dwarfs invisible to optical telescopes. Each survey added to the collective knowledge, building a census of the galaxy's contents. The investigation also extended to the Milky Way's neighbours. By studying satellite galaxies like the Large and Small Magellanic Clouds, astronomers learned about galactic interactions. Streams of stars and gas connecting these satellites to the Milky Way showed ongoing accretion, evidence that our galaxy continues to grow by consuming smaller companions. These observations placed the Milky Way in context, showing it as part of a local group of galaxies all influencing each other gravitationally. Throughout this pursuit, astronomers encountered surprises. The discovery of dark matter, inferred from the rotation of stars, revealed that most of the galaxy's mass was invisible. The identification of Sagittarius A star, the supermassive black hole at the centre, showed that the galaxy's heart was far stranger than expected. Each discovery answered questions, but also raised new ones. The investigation of the Milky Way became an ongoing process, a continuous refinement of understanding, a pursuit that would likely continue as long as humans remained curious about their cosmic home. The investigation of the Milky Way produced vast amounts of data, mountains of measurements and observations collected over decades by countless instruments. Each data point was a clue, a fragment of information about the galaxy's structure, composition, or behaviour. Individually, these fragments might seem insignificant. A single star's position, the velocity of a gas cloud, the spectrum of light from a distant cluster, but collectively they formed a picture, revealing patterns that transformed our understanding of the galaxy we call home. Distance measurements were among the most fundamental clues. Knowing how far away something is allows you to determine its true size and brightness. For nearby stars, parallax provided accurate distances. As Earth orbits the Sun, nearby stars appear to shift slightly against the more distant background, and the size of that shift reveals how far away they are. The Gaia satellite measured parallax for over 1 billion stars, creating the most precise distance map ever made. These measurements showed that the Milky Way's disk is not perfectly flat but slightly warped, bent at the edges like a record left in the sun. Stellar velocities offered another crucial set of clues. By measuring the Doppler shift in starlight, astronomers determined how fast stars were moving toward or away from us. Combined with measurements of motion across the sky, these velocities revealed orbital patterns. Stars near the galactic centre moved faster than those farther out, but the relationship between distance and velocity did not match predictions based on visible matter alone. The outer stars moved too fast. Something unseen was providing additional gravity, keeping them bound. This discrepancy became one of the strongest pieces of evidence for dark matter. Chemical compositions, revealed through spectroscopy, told stories about stellar ages and origins. Older stars, formed early in the galaxy's history, contained mostly hydrogen and helium with only trace amounts of heavier elements. Younger stars showed higher concentrations of carbon, oxygen, iron, and other elements forged in earlier generations and scattered by supernova. This chemical enrichment traced the galaxy's evolution, showing how matter cycled through stars, was expelled into space and gathered into new systems. The data showed that the Milky Way had grown more chemically complex over time. The distribution of gas and dust, mapped in radio and infrared wavelengths, revealed where new stars were forming. Dense molecular clouds appeared as dark patches in visible light but glowed in other wavelengths. Within them, protostars were collapsing, their heat radiating outward. The data showed that star formation was not uniform across the galaxy, but concentrated in spiral arms where gas was compressed. Outside the arms, formation proceeded more slowly. This pattern confirmed theoretical models of how spiral structure influenced the life cycle of the galaxy. Observations of globular clusters provided clues about the Milky Way's age and early history. These dense spheres of ancient stars, some over 13 billion years old, were among the first structures to form. Their distribution in a spherical halo suggested they predated the flattening of the disk. Chemical analysis showed they were poor in heavy elements, consistent with formation in the early universe, before many generations of stars had enriched the interstellar medium. Globular clusters were fossils, remnants of the galaxy's youth preserved into the present. Streams of stars crisscrossing the halo offered evidence of past mergers. These streams, discovered through careful analysis of stellar positions and velocities, were the torn remnants of smaller galaxies consumed by the Milky Way. The Sagittarius dwarf galaxy, for instance, was currently being pulled apart. Its stars stretched into long arcs wrapping around our galaxy. The data showed that the Milky Way had grown through accretion, absorbing dozens of smaller companions over billions of years. Each stream was a record of a collision, a fossil of galactic cannibalism. The rotation curve of the Milky Way, plotting orbital velocity against distance from the centre, became one of the most important clues. In a system where visible matter was dominant, velocity should decrease with distance following Kepler's laws. But the Milky Way's rotation curve remained flat, with stars at the edge moving as fast as those closer in. This flat curve implied a massive halo of dark matter, extending far beyond the visible disk. The data could not show what dark matter was, but it clearly showed it was there. Measurements of the galactic centre in multiple wavelengths revealed a compact source of radio emission called Sagittarius A star. Tracking stars orbiting this source showed they moved at incredible speeds, whipping around an invisible point in just a few years. The data allowed calculation of the central mass, roughly 4 million times that of the Sun, packed into a region smaller than the solar system. The only object that could have such properties was a supermassive black hole. The data proved what had been theoretical, confirming that the Milky Way's heart was one of the strangest objects in the universe. Infrared surveys revealed that the central bulge was not spherical but elongated, forming a bar of stars stretching across the galactic centre. This bar influences the orbits of nearby stars and helps channel gas toward the centre. The discovery of the bar came relatively recently, in the 1990s, showing that even basic structural features of the Milky Way remained hidden until the right data was collected. Pulsar timing provided precision measurements of stellar masses and gravitational effects. These rapidly rotating neutron stars emit regular pulses of radiation, acting as cosmic clocks. Tiny variations in pulse timing revealed the gravitational influence of companions, allowed detection of planets around distant stars, and even promised eventual detection of gravitational waves. Pulsars scattered throughout the galaxy became natural laboratories, their data probing physics at extremes impossible to replicate on Earth. All this data, collected over decades by thousands of researchers using hundreds of instruments, formed the foundation of our understanding. No single measurement revealed the Milky Way's nature. Instead, it emerged from the accumulation of clues, fragments assembled into a coherent picture. The process continues. New telescopes gather new data, refining measurements, discovering new features, correcting old assumptions. The Milky Way reveals itself slowly, one clue at a time, and each fragment of data brings us closer to knowing the full story of our galactic home. Beneath the visible Milky Way, beneath the stars and gas and dust that glow in our telescopes, lies something far stranger. For most of the 20th century, astronomers believed they understood the galaxy's basic composition. Stars made of hydrogen and helium, clouds of gas between them, dust grains scattered throughout, all bound together by gravity. This picture seemed complete, but the data kept revealing inconsistencies. Stars moved in ways that visible matter alone could not explain. The galaxy rotated as if surrounded by something unseen, something massive, something that provided gravity without light. The deeper mystery was not what we could see, but what we could not, and its discovery would transform our understanding of everything. The first hints came from rotation curves, those plots of orbital velocity versus distance from the galactic centre. According to Newton's laws, stars farther from the centre should orbit more slowly, just as outer planets in the solar system take longer to complete their orbits than inner ones. But measurements of the Milky Way showed something different. Stars at the edge moved just as fast as those closer in, their velocities remaining roughly constant across vast distances. This flat rotation curve defied expectations. Either our understanding of gravity was wrong, or something invisible was providing additional mass. Astronomers were reluctant to abandon Newton's laws. which had proven reliable for centuries. Instead, they considered the possibility of unseen matter. Perhaps the galaxy contained more material than telescopes revealed. Perhaps there were vast clouds of cold gas, too diffuse to detect, or populations of dim stars below the threshold of observation. Searches began for this missing mass, but every attempt came up short. Radio surveys found some additional gas, but nowhere near enough to explain the rotation curves. Infrared searches revealed cool stars, but again, not enough. Whatever was holding the galaxy together remained hidden. The breakthrough came from studying other galaxies. Vera Rubin and Kent Ford, working in the 1970s, measured rotation curves for dozens of spiral galaxies. Beyond the Milky Way, they found the same pattern everywhere: flat rotation curves that required far more mass than visible matter could provide. This was not a quirk of our galaxy, but a universal phenomenon. Every spiral galaxy seemed to be embedded in a halo of invisible matter. The evidence was overwhelming. Something unseen dominated the mass of galaxies, outweighing ordinary matter by factors of 5 or 10 or more. Fritz Zwicky had proposed the existence of dark matter decades earlier in the 1930s based on observations of galaxy clusters. He noticed that galaxies within clusters moved too fast to be held together by their visible mass alone. He called the missing component dark matter, matter that exerted gravity but did not emit, absorb or reflect light. At the time, his idea was largely ignored, dismissed as speculative. But Rubin's work revived it, providing concrete evidence that dark matter was real and pervasive. For the Milky Way, the implications were profound. Most of our galaxy's mass was not in stars or gas, but in a halo of dark matter extending far beyond the visible disk. This halo might stretch hundreds of thousands of light-years outward, perhaps even to the edge of the galaxy's gravitational influence. It was invisible, detectable only through its effects on the motions of stars and gas. The galaxy we saw, with its spiral arms and glowing nebulae, was just a luminous island floating in a vast dark ocean. What exactly was dark matter? That question remains one of the deepest mysteries in physics. It cannot be ordinary matter, atoms and molecules like those that make up stars and planets, because ordinary matter interacts with light. It emits radiation when heated, absorbs light when cool, reflects or scatters photons. Dark matter does none of these things. It seems to interact only through gravity, passing through ordinary matter without collision or absorption. Some unknown particle, or perhaps an undiscovered property of space itself, counts for most of the galaxy's mass. Candidates for dark matter particles have been proposed. Weakly interacting massive particles, or WIMPs, are theoretical particles that interact only through gravity and the weak nuclear force. Experiments deep underground have searched for these particles, hoping to detect rare collisions with ordinary matter, but so far without success. Axions, another candidate, are hypothetical particles predicted by certain theories of particle physics. They would be extremely light and extraordinarily abundant, filling the galaxy in numbers beyond comprehension. Sterile neutrinos, modified gravity theories, primordial black holes, all have been suggested but none confirmed. Despite not knowing what dark matter is, astronomers have mapped its distribution through gravitational effects. Computer simulations show how dark matter halos form, how they clump and merge, how they provide the scaffolding on which galaxies build. The visible Milky Way sits within a dark matter halo that shaped its formation and continues to govern its dynamics. Without this halo, the galaxy would have formed differently, if at all. The structures we see today owe their existence to the invisible framework beneath. The discovery of dark matter changed how astronomers thought about the Milky Way. What we see is not what dominates. The luminous matter, everything visible in telescopes, is only a small fraction of the total. The rest is hidden, known only through inference and calculation. This realization was humbling. For centuries, astronomers had studied light, building ever more powerful instruments to see fainter and more distant objects. But the majority of the galaxy lay beyond the reach of any telescope, invisible by its very nature. The deeper mystery also raised philosophical questions. If most of the universe is dark matter, then our experience of reality is fundamentally incomplete. We live in a cosmos where the dominant form of matter is undetectable to our senses and our instruments, present only as a gravitational influence. This is not ignorance that will be cured by better telescopes. Dark matter does not emit light. No matter how sensitive our detectors become, we will never see it directly. We can only infer its presence, map its distribution, and study its effects. Yet this hidden truth also connects us more deeply to the cosmos. The dark matter halo surrounding the Milky Way extends through the solar system, through Earth, through our bodies. At this moment, dark matter particles are passing through you, billions or trillions of them, interacting so weakly that they leave no trace. You're immersed in the unseen structure of the galaxy, part of a system far larger than the visible stars suggest. The Milky Way is not just what shines overhead, but also what flows invisibly around and through us, binding the galaxy together, shaping its past and future. The deeper mystery of dark matter remains unsolved. Experiments continue, theories evolve, and astronomers refine their understanding of how it behaves even if they do not yet know what it is. The Milky Way, in revealing this hidden truth, has shown us that the universe is stranger than we imagined, that visibility is not the same as existence, and that some of the most important truths lie not in what we can see, but in what we can deduce from its absence. In 1924, Edwin Hubble stood at the eyepiece of the Hooker telescope on Mount Wilson, California, studying photographic plates of the Andromeda Nebula. He had been tracking variable stars within it, Cepheids that brightened and dimmed with regular rhythms. These stars were valuable because their periods of variation were directly related to their intrinsic brightness. By comparing how bright they appeared to how bright they should be, Hubble could calculate their distance. When he completed the calculation, the result was staggering. Andromeda lay nearly 1 million light-years away, far beyond the boundaries of the Milky Way. It was not a nebula within our galaxy, but a galaxy in its own right. The universe had just become immensely larger. This discovery was a turning point, a moment when humanity's understanding of existence underwent a paradigm shift. For centuries, philosophers and astronomers had debated whether the Milky Way was the entire universe or just one system among many. Hubble's measurement settled the question definitively. The Milky Way was one galaxy, and beyond it lay countless others, each containing billions of stars, each separated by vast gulfs of space. The cosmos was not a single stellar system, but an archipelago of galaxies stretching as far as telescopes could see. The implications rippled through astronomy and beyond. If Andromeda was a separate galaxy, then many of the faint nebulous patches scattered across the sky must also be galaxies. Hubble and his colleagues began measuring distances to other nebulae, finding them millions or even tens of millions of light-years away. The universe was populated with galaxies, each one comparable to the Milky Way in size and complexity. The pale band of light we called home was just one among billions, a single note in a cosmic symphony. This realization recontextualized everything astronomers thought they knew about the Milky Way. It was no longer the totality of creation, but a single example of a common type of object. Comparisons became possible. How did the Milky Way rank in size compared to other spirals? Was it typical or unusual? Did all galaxies rotate as ours did? Did they all contain similar mixtures of stars, gas, and dust? The Milky Way could now be studied not in isolation but as part of a population, and that population numbered in the billions. Hubble's discovery also led to another profound insight. When he measured the spectra of distant galaxies, he found that their light was shifted toward the red end of the spectrum, an effect caused by motion away from us. The farther the galaxy, the greater the redshift. This pattern suggested that the universe itself was expanding, with galaxies receding from each other as space stretched between them. The Milky Way was not static in an unchanging cosmos, but part of a dynamic, evolving universe that had a beginning and would have a future different from its past. The paradigm shift extended to cosmology. If the universe was expanding, then tracing backward in time would lead to a moment when everything was compressed into an incredibly dense state. This idea, eventually called the Big Bang, suggested the universe had an origin, a starting point roughly 14 billion years ago. The Milky Way, then, was not eternal but ancient, formed in the aftermath of that primordial explosion as matter condensed into galaxies. Our galaxy had a history, a narrative arc from birth to the present, and eventually to whatever lay ahead. Understanding the Milky Way as one galaxy among many also changed how astronomers approached its study. They could observe other spirals, seeing them from outside, and use those observations to infer what our own galaxy must look like. They noticed that spiral galaxies came in variations, some with tight arms, some with loose, some with prominent central bars, others without. Where did the Milky Way fit in this taxonomy? Was it a typical spiral or something distinctive? These questions could only be asked once astronomers understood that galaxies were numerous and varied. The turning point also affected how humanity saw itself. The realization that Earth orbited the Sun had displaced us from the centre of the solar system. The understanding that the Sun was an ordinary star among billions had displaced us from any privileged position within the Milky Way. Now, the discovery that the Milky Way was one galaxy among billions displaced us again, pushing humanity further from centrality. We lived in an ordinary location within an ordinary galaxy, within an ordinary region of an unimaginably vast universe. Each step outward was a step toward humility. Yet this shift was also empowering. To understand the Milky Way's place in the universe was to understand our place within it. We were not isolated, but connected to a cosmic web of galaxies, all evolving together, all shaped by the same physical laws. The light from distant galaxies carried information about conditions billions of years ago, allowing astronomers to reconstruct the history of the universe itself. The Milky Way became not just our home, but a laboratory for studying cosmic evolution. The turning point marked by Hubble's discovery accelerated the pace of astronomical research. Telescopes grew larger, instruments more sensitive, techniques more sophisticated. The universe revealed itself as far more complex than anyone had imagined. Galaxies collided and merged. Clusters formed vast structures connected by filaments of dark matter. The cosmos had architecture on scales that dwarfed individual galaxies, and the Milky Way, once thought to be everything, was now understood as a single thread in a vast tapestry. This paradigm shift also changed how people thought about the Milky Way in everyday life. It was no longer mysterious in the old sense, no longer the subject of myths about rivers of milk or paths of spirits. It was a galaxy, a specific type of object that could be studied and understood. Yet in becoming comprehensible, it had also become more wondrous. To know that the pale band overhead was a spiral of hundreds of billions of stars, one among billions of such spirals, was to grasp a truth far stranger than any ancient myth. The turning point of 1924 did not answer all questions. It opened new ones. How do galaxies form? How do they evolve? What determines their shapes and sizes? What role does dark matter play? Each question led to decades of research, but the foundation had been laid. The Milky Way was no longer the universe but our galaxy, our home, within a cosmos far larger and far older than anyone had dreamed. This shift in perspective from everything to one among many was perhaps the most profound change in human understanding since the realization that Earth was not flat. The Milky Way remained our home, but now we knew that home was part of an immensely larger structure, and that knowledge changed everything. The discovery that the Milky Way was just one galaxy among billions sent immediate ripples through the scientific community and beyond. Textbooks had to be rewritten. Astronomical catalogues had to be reorganized. The vocabulary of cosmology had to be revised. What had been called nebulae were now understood as galaxies, island universes in their own right. What had been thought of as the edge of existence was now understood as merely the limit of observation. The consequences were practical, philosophical, and profound, touching every aspect of how humanity understood its place in the cosmos. For astronomers, the immediate consequence was a shift in research priorities. If galaxies were the fundamental building blocks of the universe, then understanding them became paramount. How did they form? How did they evolve? What determined whether a galaxy became a spiral like the Milky Way, or an elliptical like those Hubble was also observing? These questions required new observational programs, new theoretical frameworks, and new ways of thinking about structure on cosmic scales. The Milky Way became not the subject of study but one example among many, a reference point for comparison. The ripple extended to physics. If the universe was expanding as Hubble's redshift measurement suggested, then the laws governing that expansion had to be understood. Einstein's general theory of relativity, published less than a decade before Hubble's discovery, provided the mathematical framework for describing an expanding universe. But Einstein himself had initially resisted the idea, adding a cosmological constant to his equations to keep the universe static. Hubble's observations showed that resistance was unfounded. The universe was dynamic, and understanding its evolution became a central challenge for theoretical physics. The immediate practical consequence for observing the Milky Way was renewed urgency. If our galaxy was just one among billions, then studying it offered insights into all galaxies. But it also meant that understanding the Milky Way required comparing it to others. Astronomers began systematic surveys of galaxies, cataloguing their properties, measuring their distances, analysing their spectra. Each observation of a distant spiral informed understanding of our own. Each measurement of galactic rotation curves, star formation rates, or chemical compositions added to the growing picture of what galaxies were and how they behaved. The consequence for cosmology was revolutionary. If galaxies were spread throughout an expanding universe, then tracing backward in time led to a moment when they were all much closer together, when the universe itself was smaller, denser, hotter. This realization gave birth to Big Bang cosmology, the idea that the universe had an origin point roughly 14 billion years ago. The Milky Way, in this new framework, was not eternal but ancient, formed when the universe was still young, when the first structures condensed out of the primordial gas. For education and public understanding, the consequence was a dramatic shift in how the cosmos was presented. Planetariums and museums updated their exhibits. Popular books revised their descriptions of the universe. The image of the Milky Way as a spiral galaxy viewed from afar, though an artistic representation rather than a photograph, became iconic. People began to grasp that the pale band overhead was not just a collection of stars but a structured system, comparable to the distant spirals visible through telescopes. The Milky Way was brought into focus as an object, not just an experience. Philosophically, the consequence was profound. Humanity had already been displaced from the centre of the solar system, and then from any special position within the galaxy. Now we were displaced again, from the centre of the universe, because there was no centre. The Milky Way was one galaxy in a vast expanse where all galaxies were receding from all others. There was no privileged location, no cosmic throne from which to observe everything. We were situated in one ordinary galaxy among billions, and that ordinariness was itself a kind of truth about existence. Religious and cultural responses varied. Some found the expansion of the cosmos exhilarating, seeing in it evidence of divine creativity on scales previously unimagined. If God had created billions of galaxies, each with billions of stars, then surely that demonstrated infinite power and majesty. Others found it disquieting, struggling to reconcile traditional teachings about humanity's significance with the new understanding of our marginal position. These tensions played out in sermons, essays, and public debates, reflecting deeper questions about meaning in an immense universe. The consequence for scientific institutions was increased funding and support for astronomy. Observatories expanded, new telescopes were planned and built. Universities hired more astronomers to study galaxies, cosmology, and the large-scale structure of the universe. The Mount Wilson telescope that Hubble used became famous, but it would soon be joined by others, each larger and more powerful. The momentum created by the paradigm shift drove decades of astronomical research, establishing the field as a major scientific discipline. For individual scientists, the consequence was often personal. Those who had argued that the Milky Way was the entire universe had to revise their views, sometimes publicly and with difficulty. Those who had suspected the existence of external galaxies found their positions vindicated, but also faced new responsibilities to explain and expand on the discovery. The scientific process, with its requirement for evidence and revision, played out in real time, showing both the strength of the method and the human challenges of changing deeply held beliefs. The immediate ripple also affected how the Milky Way was mapped. If our galaxy was comparable to Andromeda, then studying Andromeda's structure could inform models of our own. Astronomers began measuring the Milky Way's size more carefully, refining estimates of stellar populations, tracing the distribution of gas and dust. The goal was not just to describe the Milky Way, but to understand how it fit into the broader population of galaxies. Was it large or small, young or old, active in star formation or quiescent? Each question had comparative context now, a frame of reference that had not existed before. Consequence extended even to language. Terms like universe, cosmos, and galaxy had to be defined more precisely. The Milky Way was a galaxy. The universe contained billions of them. The cosmos referred to everything, all matter, energy, and space. These distinctions, once blurred, became important as astronomy grew more sophisticated. Clarity in language reflected clarity in understanding, and both were consequences of the turning point that Hubble's discovery represented. In the decades following 1924, the ripples continued to spread. New observations confirmed and extended Hubble's findings. Galaxies were found at ever greater distances, their light stretched by the expansion of space. The Milky Way remained our home, familiar and central to human experience, but now understood as part of an incomprehensibly larger system. The immediate consequence of that understanding was a transformation in how we saw ourselves, a shift that continues to shape astronomy, philosophy, and culture to this day. The realization that the Milky Way was one galaxy among billions did not remain confined to 1924, or even to the decades immediately following. Its impact echoed through time, shaping every subsequent generation's understanding of the cosmos. The discovery became foundational, a pivot point in human knowledge that affected not just astronomy, but biology, philosophy, technology, and even art. To understand the Milky Way as one galaxy was to understand existence differently, and that understanding reverberated across disciplines and cultures. In astronomy, the impact was transformative. The field restructured itself around the study of galaxies as fundamental objects. Entire careers were devoted to understanding galactic formation, evolution, and dynamics. Observatories prioritized surveys that catalogued thousands and eventually millions of galaxies. Each observation added to the statistical understanding of how galaxies behaved, how common different types were, how they clustered in space. The Milky Way became both subject and context, studied in detail while also serving as a reference for interpreting distant observations. The impact on cosmology was equally profound. Understanding that galaxies were distributed throughout an expanding universe led to the development of Big Bang theory, the standard model of cosmic evolution. This theory explained not just the expansion but also the formation of light elements, the cosmic microwave background radiation, and the large-scale structure of the universe. The Milky Way's place in this narrative was as a product of cosmic evolution, a structure that condensed from primordial gas and grew through billions of years. Every aspect of our galaxy, from its oldest stars to its ongoing star formation, could be understood within this temporal framework. The biological impact came through astrobiology, the study of life in cosmic context. If the Milky Way contained hundreds of billions of stars, and if most stars had planets, then the potential for life elsewhere became not just possible but probable. The Drake equation, formulated in 1961, attempted to estimate the number of communicable civilizations in the galaxy. Though the parameters remained uncertain, the equation itself reflected how understanding the Milky Way as one galaxy among many had opened questions about life's prevalence. We were one example of life on one planet around one star in one galaxy. Were there others? The question became scientifically tractable, inspiring searches for extraterrestrial intelligence and missions to study exoplanets. Philosophically, the impact was a continued erosion of anthropocentrism. The Copernican revolution had removed Earth from the centre of the solar system. Darwin's theory of evolution had removed humanity from a special category of creation. The realization that the Milky Way was ordinary within a universe of billions of galaxies continued this trend. We were not central, not unique in location, and possibly not alone. This perspective, sometimes called the Copernican principle or the principle of mediocrity, suggested that our situation was typical rather than exceptional. The philosophical implications were debated in universities, written about in essays, and incorporated into how educated people understood their place in existence. Technologically, the impact drove innovation. Better telescopes were needed to study distant galaxies, so optics improved. photographic plates gave way to electronic detectors, greatly increasing sensitivity. Radio astronomy, infrared astronomy, X-ray astronomy, all developed partly to study galaxies in different wavelengths. Space-based observatories like Hubble, Spitzer, and Chandra were launched to avoid atmospheric distortion. Each technological advance was driven partly by the desire to understand galaxies, including our own. The impact of that drive extended beyond astronomy, influencing fields like materials science, computer processing, and data analysis. The cultural impact appeared in literature, film, and art. Science fiction writers placed civilizations throughout the Milky Way, imagining a galactic community of species spread across thousands of light years. Films depicted space travel between stars, galactic empires, and encounters with alien intelligences. These stories, while fictional, reflected the shift in perspective that came from understanding the Milky Way as a vast system filled with stars and possibilities. The galaxy became a setting, a stage on which human imagination could play out scenarios of exploration, conflict, and discovery. Educational systems incorporated the new understanding into curricula. Children learned that the Milky Way was a spiral galaxy, that it contained billions of stars, that the Sun was located in one of its outer arms. This knowledge became basic literacy, part of what it meant to be educated about the natural world. Generations grew up with a fundamentally different cosmological framework than their grandparents, seeing the universe as vast, ancient, and populated with galaxies. The impact on collective consciousness was gradual but deep. The impact also extended to how we thought about time. If the universe was 14 billion years old and the Milky Way formed relatively early in that history, then our galaxy had witnessed most of cosmic time. Stars had been born, lived, and died for billions of years before the Sun formed. The atoms in our bodies were forged in those earlier stars, scattered by supernova, and recycled into new systems. Understanding the Milky Way's age placed human existence in temporal context. We were latecomers, appearing in the last fraction of the galaxy's history, living in a mature system already shaped by billions of years of evolution. Religious thought adapted, though not uniformly. Some theologians embraced the expanded cosmos, arguing that a God capable of creating billions of galaxies was more worthy of worship than one who created only a single world. Others struggled with the implications, trying to reconcile traditional teachings about humanity's central importance with the new understanding of our marginal location. The impact on religious thought was complex, varying by tradition and individual interpretation, but it was undeniable that the Milky Way's true nature required theological responses. Scientific institutions felt the impact through increased prestige and funding. Astronomy became a high-profile field, attracting talented researchers and substantial investment. The quest to understand galaxies, including our own, justified the construction of massive telescopes and sophisticated instruments. Nobel Prizes were awarded for discoveries related to cosmic expansion, the Big Bang, and galactic structure. The impact elevated astronomy from a niche discipline to a central part of humanity's quest to understand nature. The impact on international collaboration was significant. Studying distant galaxies required large telescopes and complex instruments that often exceeded the resources of single nations. Collaborations formed, pooling expertise and funding. The European Southern Observatory, the international partnerships that built the Hubble Space Telescope, and multinational efforts to detect gravitational waves all reflected how understanding the cosmos had become a shared human endeavour. The Milky Way, and the billions of galaxies beyond it, belonged to everyone. In the end, the impact of understanding the Milky Way as one galaxy among billions cannot be measured in any single metric. It reshaped how humanity saw itself, how science progressed, how technology developed, how culture expressed cosmic themes. The echoes through time continue, each generation building on the knowledge established by Hubble's discovery and the work that followed. We live in a different conceptual universe than our ancestors did a century ago, and that difference stems largely from understanding our place within the Milky Way and the Milky Way's place within the cosmos. Behind every discovery about the Milky Way stand individuals, people who dedicated their lives to understanding our cosmic home. These were not figures of mythology, but real scientists, observers, theorists, each bringing their particular vision to the study of the galaxy. Some achieved fame, others laboured in obscurity, but all contributed to the slow accumulation of knowledge that transformed the Milky Way from myth to science. To understand the galaxy is also to understand the dreamers who made that understanding possible. Galileo Galilei represents the beginning. In 1610 he turned his telescope skyward and saw what no one had seen before. The Milky Way resolved into stars, countless points of light crowding the field of view. Galileo was not primarily interested in the Milky Way. His major work focused on the planets and the moon, but his observation of the galactic band was recorded and became foundational. He was a dreamer who believed instruments could extend human perception, revealing truths hidden from the naked eye. His dream was vindicated not in his lifetime, but across the centuries that followed. William Herschel, working in the late 1700s and early 1800s, was perhaps the first true student of the Milky Way. He built his own telescopes, some of the largest and best of his era, and used them to count stars systematically. Herschel wanted to map the galaxy, to determine its shape and size. He worked with his sister Caroline, herself an accomplished astronomer, cataloguing thousands of objects. Herschel's dream was to create a complete picture of the sidereal system, and though his maps were incomplete, limited by dust he could not detect, his systematic approach set standards for observational astronomy. Harlow Shapley, in the early 20th century, revolutionised understanding of the Milky Way's scale and structure. By studying globular clusters, those ancient spheres of stars orbiting in the halo, Shapley determined their distances and distribution. He noticed they were not centred on the Sun, but on a point thousands of light-years away in the direction of Sagittarius. This meant the Sun was not at the galaxy's centre, but far out in the disk. Shapley's dream was to locate humanity's true position, and in doing so he displaced us once again, showing that even within our own galaxy we occupied no special place. Henrietta Leavitt, whose work was crucial to Shapley's discoveries, exemplified the often overlooked contributions of women in astronomy. Working at Harvard Observatory as a human computer, analysing photographic plates, Leavitt discovered the relationship between the period and luminosity of Cepheid variable stars. This relationship became the cosmic distance ladder, allowing astronomers to measure distances to faraway objects. Leavitt never received widespread recognition during her lifetime, but her dream, to find order in the patterns of variable stars, unlocked one of the most important tools in galactic astronomy. Edwin Hubble, who proved that galaxies existed beyond the Milky Way, was driven by a dream of measuring the universe. He was methodical, careful, and persistent, spending night after night at the eyepiece gathering data. When he found Cepheids in Andromeda and calculated its distance, he did not immediately proclaim a revolution. He checked his work, verified his results, and only then published. Hubble's dream was precision, and his insistence on accurate measurement established the modern understanding of the cosmos. Vera Rubin, studying galaxy rotation curves in the mid-20th century, uncovered evidence for dark matter that transformed our understanding of the Milky Way. She faced obstacles as a woman in a male-dominated field, but her dream was to understand how galaxies rotated. Her observations showed that visible matter could not account for the motion she measured. Something unseen had to be present. Rubin's work, along with that of Kent Ford, her collaborator, provided the clearest evidence for dark matter's existence. Her dream was not to discover something new, but to measure something accurately, and in pursuing that dream she revealed one of the universe's deepest mysteries. Jan Oort, a Dutch astronomer, mapped the Milky Way using radio observations of hydrogen gas. Working in the mid-20th century, Oort showed how radio astronomy could peer through the dust that blocked optical observations. He traced spiral arms, measured galactic rotation, and helped establish the Milky Way structure. Oort's dream was to see the invisible, to use wavelengths beyond human perception to reveal what had been hidden. His work demonstrated that understanding required looking beyond the narrow range of visible light. Margaret Burbidge and Geoffrey Burbidge, along with William Fowler and Fred Hoyle, worked out how elements were forged in stars. Their 1957 paper explained stellar nucleosynthesis, showing how the fusion processes in stars created the elements of the periodic table. This work connected the Milky Way stars directly to the matter that makes up planets and life. The Burbidge's dream was to understand not just where stars came from, but where everything came from, and their work showed that we are literally made of stardust. Jocelyn Bell Burnell discovered pulsars while a graduate student in 1967. These rapidly spinning neutron stars, remnants of supernova, became tools for probing the Milky Way's structure. Though the Nobel Prize for the discovery went to her advisor, Bell Burnell's dream of detecting unusual signals led to one of the most important finds in 20th century astronomy. Pulsars revealed extreme physics and provided natural laboratories scattered throughout the galaxy. The scientists working on the Gaia mission represent a more recent generation of dreamers. Launched in 2013, Gaia has measured the positions and motions of over 1 billion stars, creating the most detailed map of the Milky Way ever made. The team behind Gaia, hundreds of researchers across multiple countries, share a dream of precision on an unprecedented scale. Their work continues, refining our understanding of the galaxy's structure with each data release. Behind all these named individuals were thousands of others, technicians who built instruments, observers who spent cold nights at telescopes, theorists who developed models, programmers who analysed data. The Milky Way's secrets were unlocked not by solitary geniuses, but by communities of people, each contributing their expertise. The human element in galactic astronomy is collective as much as individual, a shared dream of understanding our place in the cosmos. These dreamers were motivated by different things. Some sought knowledge for its own sake, others wanted to solve specific problems. Some were driven by competition, others by collaboration. But all shared a willingness to dedicate significant portions of their lives to studying something they could never visit, never touch, barely even see. The Milky Way existed only as data, as photographs and spectra, as measurements and calculations. Yet these dreamers treated it as real as anything on Earth, worthy of lifetimes of effort. Their dream was humanity's dream, to know where we come from, what surrounds us, and what our home truly is. Every major shift in understanding the Milky Way faced opposition. This was not mere stubbornness or ignorance, but reflected deeper patterns in how knowledge advances. New ideas challenged existing frameworks, contradicted established theories, and required abandoning familiar explanations. Opposition came from respected scientists who had built careers on older models, from institutions resistant to change, and from cultural forces uncomfortable with implications of new discoveries. The battle for truth about the Milky Way was fought not just with telescopes and data, but with arguments, debates, and sometimes bitter disputes. When Galileo announced that the Milky Way was made of stars, not everyone accepted the claim. Some argued that the telescope distorted reality, creating illusory points of light where none existed. The instrument was new, poorly understood, and its optical properties imperfect. Could it be trusted? Perhaps the Milky Way really was a luminous cloud, and the telescope merely broke that cloud into false images. This skepticism was not entirely unreasonable. Early telescopes did produce aberrations, and without a theoretical understanding of optics, trusting them required a leap of faith. The opposition forced Galileo and others to verify observations repeatedly, using different instruments until the evidence became overwhelming. The debate over the Milky Way's size and structure in the 19th and early 20th centuries produced fierce disagreements. William Herschel's maps placed the Sun near the centre of a relatively small system. Later observations suggested a much larger galaxy, with the Sun offset from the centre. When Harlow Shapley proposed in 1918 that the galaxy was 100,000 light-years across, with the Sun far from the centre, he faced opposition from those who found such scales unbelievable. How could distances be measured so precisely? Might the methods be flawed? Shapley's use of Cepheid variables to measure distances to globular clusters was innovative but unproven. Critics questioned whether Cepheids truly were reliable distance indicators, or whether other factors might affect their brightness. The great debate of 1920 between Shapley and Heber Curtis illustrated how respected scientists could interpret the same evidence differently. Shapley argued for a single vast Milky Way encompassing all visible structures. Curtis argued for a smaller Milky Way with external galaxies beyond it. Both presented compelling arguments. Both had evidence supporting their positions. The debate did not resolve the issue because the decisive data, Hubble's distance measurements to Andromeda, had not yet been obtained. Opposition between competing theories is natural in science. driving researchers to gather better evidence and refine arguments. When Hubble proved that Andromeda was a separate galaxy, some astronomers remained sceptical. The distances he calculated seemed impossibly large. Could systematic errors have crept into the measurements? Might Cepheid variables behave differently in other galaxies than they did in the Milky Way? These doubts faded as more galaxies were measured and the pattern held, but initial opposition reflected legitimate caution about revolutionary claims. Science requires extraordinary evidence for extraordinary claims, and Hubble's assertion that the universe was filled with galaxies qualified as extraordinary. The most sustained opposition came over dark matter. When rotation curves suggested that galaxies contained far more mass than visible matter could provide, many astronomers resisted the idea of invisible matter. Perhaps the measurements were wrong. Perhaps the rotation curves had been misinterpreted. Perhaps Newton's laws needed modification at galactic scales. Alternative theories like modified Newtonian dynamics, or MOND, proposed that gravity behaved differently in weak fields, eliminating the need for dark matter. The opposition to dark matter persisted for decades, driven partly by the troubling implications of admitting that most of the universe was made of something unknown. Even today, dark matter remains controversial in some quarters. Experiments have failed to detect dark matter particles directly, leading some to question whether it exists at all. Might cosmologists be chasing a phantom, inventing invisible matter to save theories rather than admitting the theories themselves need revision? This opposition keeps researchers honest, forcing them to consider alternatives and justify why dark matter remains the best explanation. The battle is not over, though the evidence for dark matter has become overwhelming. Opposition also came from outside science. Religious authorities in Galileo's time opposed heliocentrism and the idea that stars were other suns, seeing these concepts as challenges to scripture. Similar resistance met later discoveries. If the Milky Way was one galaxy among billions, if the universe was vast and ancient, if humanity occupied no special location, then what did that mean for religious teachings about creation and our significance? These concerns manifested as opposition to teaching cosmic evolution in schools, debates about the compatibility of science and faith, and cultural resistance to accepting our marginal cosmic status. Cultural opposition often worked through funding and institutional support. If powerful figures opposed certain ideas, they could limit resources available to researchers pursuing those ideas. Observatories might not allocate telescope time, grants might not be awarded, publications might be delayed. This structural opposition, less visible than open debate, nonetheless shaped which questions got investigated and which remained unexplored. The battle for truth occurred not just in academic journals but in committees deciding resource allocation. Some opposition came from honest confusion. The Milky Way's true nature was genuinely difficult to grasp. We live inside it, viewing it from within, and that limitation makes comprehensive understanding challenging. When different observations seemed contradictory, when models failed to match data, when new discoveries overturned established ideas, people naturally hesitated to accept new explanations. This opposition from confusion required education, clear communication, and patience, helping people understand how evidence led to conclusions. The opposition to new ideas about the Milky Way was not monolithic. Different people resisted for different reasons. Methodological caution, theoretical commitment, religious conviction, institutional inertia, or simple disbelief. But opposition played a constructive role. It forced proponents to strengthen their arguments, gather more evidence, and consider alternative explanations. Science advances not despite opposition but partly because of it. The dialectic between claim and counterclaim, between thesis and antithesis, drives towards synthesis, toward better understanding built on firmer foundations. The battle for truth about the Milky Way continues. Every new observation brings potential challenges to existing models. Every theory faces scrutiny from those seeking to test its limits. This is not a weakness, but a strength. The Milky Way's secrets surrender slowly, and only to those willing to face opposition, answer critics, and prove their claims with evidence. The dreamers who advanced our understanding succeeded not by avoiding opposition, but by overcoming it, by making their case so compellingly that even skeptics were eventually convinced. The battle is perpetual, but through it, truth gradually emerges. Somewhere between the accumulation of facts and the resolution of debates, a shift occurred in human consciousness. It was not sudden, not marked by a single moment or announcement, but gradual, emerging across generations as knowledge about the Milky Way seeped into collective awareness. People began to grasp not just intellectually but viscerally what it meant to live in a galaxy, to orbit within a vast spiral system, to be part of something so immense that light took 100,000 years to cross it. This awakening transformed how we saw ourselves, how we related to the night sky, and how we understood existence itself. The awakening began with images. When astronomers pointed telescopes at other spiral galaxies and captured their graceful forms, those photographs served as proxies for the Milky Way. People could look at Andromeda or the Whirlpool galaxy and imagine that our own galaxy appeared similar from outside. These images were not abstractions but visual evidence of structures containing billions of stars, each star potentially surrounded by planets. The spirals were beautiful, elegant, and immense. To realise that we lived inside such a structure, that every night the band overhead represented our view from within a spiral arm, was to experience a shift in perspective, a reorientation of thought. The awakening deepened with the understanding of scale, 100,000 light-years across, 400 billion stars, clouds of gas spanning light-years, a supermassive black hole at the centre. These numbers, repeated in textbooks and documentaries, gradually became more than statistics. They became impressions of vastness, of a home so large that human experience could barely touch it. Yet this vastness was not alien. It was our neighbourhood. The stars we saw at night were fellow members of the Milky Way, neighbours separated by light, years but bound by the same gravity, orbiting the same centre, participating in the same grand rotation. This awareness brought with it a kind of cosmic humility. To understand that we occupied one small world around one ordinary star in one outer arm of one galaxy was to confront the limits of human significance. Yet paradoxically, this humility was accompanied by a sense of connection. We were not separate from the Milky Way, but made of it. Every atom in our bodies had been forged in its stars. We were the galaxy made conscious, the Milky Way looking back at itself. This dual awareness of being both insignificant in scale and significant in consciousness became a defining feature of modern cosmological thought. The awakening also included recognizing time. The Milky Way was not static but ancient, over 13 billion years old, formed when the universe was young. Stars had been born, had lived, and had died for billions of years before the sun condensed from a cloud of gas. The atoms that make up Earth, that make up living things, had cycled through multiple generations of stars. To understand this temporal depth was to realise that we were not just somewhere in the galaxy but somewhen, appearing late in its history, living in a mature system already shaped by eons of evolution. Time became as important as space in understanding our place. Education played a crucial role in the awakening. Children who learned about the Milky Way in school grew up with a fundamentally different cosmic framework than previous generations. They knew Earth was a planet, knew the Sun was a star, knew the Milky Way was a galaxy. This knowledge became foundational, part of basic literacy about the natural world. Adults who encountered these ideas later in life often experienced a sense of revelation, a reconfiguration of their understanding. The awakening spread through populations as knowledge diffused through education systems, books, television, and eventually the internet. Visualization technology accelerated the awakening. Planetarium shows projected the night sky onto domes, allowing people to see the Milky Way as it appeared from dark locations, free from light pollution. Computer simulations showed how the galaxy rotated, how spiral arms formed and dissolved, how stars orbited the centre. Virtual reality began to offer immersive experiences of flying through the Milky Way, approaching nebulae, circling black holes. These technologies translated abstract knowledge into experiential understanding, making the galaxy feel more real, more immediate. The awakening had emotional dimensions. Many people reported feeling awe when truly grasping the Milky Way's nature for the first time. Some felt loneliness, confronting the vast distances between stars and the isolation of our small planet. Others felt wonder, marvelling at the complexity and beauty of galactic structure. Still others felt belonging, recognising that we were part of something larger than ourselves, connected to the cosmos in fundamental ways. These emotional responses were not separate from scientific understanding, but integral to it, shaping how knowledge was internalised and what it meant personally. Art and culture reflected and amplified the awakening. Painters incorporated galactic themes into their work. Musicians composed pieces inspired by cosmic scales. Writers placed stories throughout the Milky Way, imagining civilizations on distant worlds, travellers journeying between stars, encounters with the alien and unknown. Science fiction became a medium through which people explored what it meant to live in a galaxy, to be one species among potentially many, to navigate vast spaces and deep time. These cultural expressions helped translate scientific knowledge into shared human experience. The awakening also brought existential questions. If we were so small, so marginal in location, did our lives have meaning? If the universe was so vast, so filled with galaxies, could individual existence matter? These questions did not have simple answers, but wrestling with them became part of modern philosophical thought. Some found meaning in connection, in being part of the cosmic whole. Others found it in consciousness itself, in the remarkable fact that matter had organised into forms capable of understanding. The awakening included not just knowing about the Milky Way, but integrating that knowledge into frameworks of meaning. Environmentalism drew on the awakening in unexpected ways. Images of Earth from space, showing our planet as a small blue marble against the darkness, conveyed fragility and isolation. Understanding Earth as one world among countless others in the Milky Way reinforced how precious and rare our circumstances were. The galaxy contained billions of planets, but we knew only one that harboured life. This awareness informed conservation efforts, arguments for protecting ecosystems, and calls to treat Earth as the unique home it represented. The cosmic perspective made terrestrial concerns more urgent, not less. The awakening was not complete or universal. Many people went through life without deeply considering the Milky Way or what it meant. Daily concerns, immediate realities, local contexts dominated attention. But for those who engaged with the knowledge, who looked up at the night sky with understanding, who grasped that the pale band overhead was our view from inside a galaxy, the awakening was real. It changed how they saw the world, how they understood themselves, and how they related to the cosmos. This shift in awareness, spreading gradually through populations, represented a milestone in human consciousness, a recognition of our place within the vast structure we call home. Among all the discoveries about the Milky Way, one stands as the most profound, the most intimate, the most personally relevant. It is not a measurement of distance or mass, not a map of spiral arms or a catalogue of stars. It is the realization that we are made of the galaxy itself. Every atom in your body, every molecule that forms your cells, every element that makes you possible, was created in stars and scattered through the Milky Way. You're not a visitor to this galaxy, not a passenger travelling through it. You are part of it, assembled from its material, shaped by its history, living briefly as one expression of matter that has been cycling through the cosmos for billions of years. This revelation emerged gradually as astronomers worked out how elements were formed. In the early universe, just after the Big Bang, only the lightest elements existed: hydrogen, helium, and traces of lithium. Everything else, every element heavier than lithium, had to be created later. The question of where and how occupied physicists and astronomers for decades. The answer, worked out in the mid-20th century, was that stars were the factories. In their cores, under immense pressure and temperature, nuclear fusion combined light elements into heavier ones. Hydrogen fused into helium. Helium fused into carbon and oxygen. Carbon and oxygen combined into neon, magnesium, silicon. The process continued up the periodic table, building heavier and heavier elements. But fusion alone was not enough. These newly created elements remained locked inside stars unless something released them. That something was stellar death. When massive stars exhausted their fuel, they exploded as supernova, blasting their enriched contents into space. These explosions were violent beyond comprehension, releasing as much energy in a few weeks as the sun produces in its entire lifetime. The shockwaves scattered elements across light years, seeding the interstellar medium with carbon, nitrogen, oxygen, iron, and dozens of others. Smaller stars contributed too, shedding their outer layers as planetary nebulae, returning material to the galaxy more gently but still significantly. This meant that the galaxy was not static in composition, but evolving chemically. Each generation of stars enriched the interstellar medium with heavier elements. The first stars, formed from primordial gas, contained almost no heavy elements. When they died, their ejecta mixed with surrounding hydrogen. The second generation of stars formed from this enriched material, containing traces of carbon, oxygen, and iron. They lived, died, and enriched the medium further. The cycle repeated billions of times, gradually increasing the concentration of heavy elements throughout the Milky Way. Our Sun formed about 4.5 billion years ago from a cloud of gas already enriched by countless earlier generations. That cloud contained hydrogen and helium, yes, but also significant amounts of heavier elements. When the Sun ignited, leftover material in the surrounding disk condensed into planets. Rocky worlds like Earth formed from the heavier elements: iron, silicon, oxygen, magnesium. Gas giants like Jupiter collected lighter elements: hydrogen and helium, along with smaller amounts of heavier compounds. Every bit of this material, every atom in the entire solar system, came from previous stars. The revelation becomes personal when you trace specific elements to their origins. The calcium in your bones was created in massive stars through fusion processes. When those stars exploded, calcium scattered into space and eventually became part of the molecular cloud from which the solar system formed. The iron in your blood has a similar story, forged in the cores of dying stars and dispersed by supernova. The oxygen you breathe was created through helium fusion in stars somewhat less massive than those that made iron. The carbon that forms the backbone of every organic molecule in your body came from the stars that lived and died before the Sun was born. Even the hydrogen in your body has a cosmic origin, though more ancient. Hydrogen atoms date back to the Big Bang itself, formed in the first minutes of the universe when conditions were right for protons and electrons to combine. The hydrogen in water, in your cells, in every organic compound, is 13.8 billion years old, nearly as old as the universe. When you drink water, you're consuming atoms that have existed since cosmic dawn, that have passed through clouds, oceans, and living things countless times, that may once have been part of stars before being returned to the interstellar medium. This revelation connects you directly to the Milky Way's history. You're not made of new material, but of recycled matter, atoms that have been through multiple stars and cycles. The galaxy is not a backdrop to your existence, but the source of it. Without stellar nucleosynthesis, without supernova to scatter elements, without the billions of years of chemical enrichment, there would be no rocky planets, no complex chemistry, no life. The Milky Way created the conditions for your existence through processes playing out across its volume over cosmic time. The revelation also means that you're related to everything else in the galaxy. The stars overhead are not just distant objects, but relatives, family members in a cosmic sense. They were made from the same material, shaped by the same processes. Some of the atoms in your body may have once been part of those stars. Some atoms currently in distant stars may one day be part of future beings on future worlds. The boundaries between self and galaxy dissolve when you recognise that you are a temporary arrangement of galactic matter, atoms borrowed briefly from the Milky Way and destined to return. This understanding transforms how the night sky feels. When you look up at stars, you're looking at the furnaces that created you. The pale band of the Milky Way represents not just your location, but your origin. Every element necessary for life was forged in stars scattered throughout that band. You are the Milky Way looking at itself, matter organised by evolution into a form capable of consciousness, able to recognise its cosmic heritage. This recursive quality, the galaxy producing beings that can understand the galaxy, is perhaps the deepest revelation of all. The revelation has philosophical weight. It suggests that life is not separate from the cosmos, but integral to it. We are not visitors in a universe foreign to us. We are expressions of cosmic evolution, as natural as stars or galaxies. The same physical laws that govern stellar fusion and galactic rotation also govern biochemistry and thought. There is no fundamental divide between living and non-living, between terrestrial and cosmic. Everything is made of the same stuff, following the same rules, connected by shared material origins. Some find this revelation comforting. To be made of stars is to belong to something grand, to have origins beyond Earth, to be part of a story billions of years in the making. Others find it humbling, recognizing that individual existence is brief, that the atoms making you up have been and will be part of countless other forms. But whether comforting or humbling, the revelation is undeniable. It is written in spectroscopy, confirmed by nuclear physics, demonstrated by astronomy. You are stardust, not metaphorically but literally, and the Milky Way is the system that made you possible. With the facts established, with the data collected and the theories tested, a space opens for reflection. What does it mean to live in the Milky Way? What significance does our galactic home hold beyond the measurements and observations? These questions do not have single answers, but invite contemplation, a slowing down to consider implications rather than rushing toward new discoveries. The Milky Way is not just an object of study, but a context for existence, an understanding that context changes how we see everything else. One reflection centres on scale. The Milky Way is so vast that light takes 100,000 years to cross it, yet it is just one galaxy among billions. Within it are 400 billion stars, yet our Sun is unremarkable among them. The galaxy contains nebulae larger than solar systems, clusters older than most stars, and a black hole millions of times more massive than the Sun. Yet these features are typical of spiral galaxies. Scale, when truly grasped, induces a particular kind of vertigo, a recognition that the categories of large and small we apply in daily life barely touch cosmic reality. Yet scale is not the whole story. The Milky Way is also comprehensible. We can map it, model it, understand its structure and evolution. This comprehensibility is remarkable. The galaxy is not chaotic or random, but organised by physical laws we can discover and describe. Gravity shapes its structure. Nuclear fusion powers its stars. Chemistry enriches its gas. Everything follows rules, and those rules can be known through patient observation and careful thought. The reflection here is on the intelligibility of nature, on the fact that the universe can be understood by minds that are themselves products of that universe. Another reflection considers time. The Milky Way is ancient, over 13 billion years old, formed when the universe was in its infancy. Human civilization, in contrast, spans perhaps 10,000 years. The entire history of our species, from the first anatomically modern humans to the present, covers less than a millionth of the galaxy's lifetime. We are latecomers, appearing in the final pages of a long story. This temporal perspective can feel diminishing, but it can also feel enriching. We are part of something far older and more enduring than ourselves, connected to a history that stretches back almost to the beginning of time. Reflection on our location within the Milky Way reveals a kind of cosmic mediocrity that is also a form of safety. We are not at the centre, not in the densest regions where stellar collisions and intense radiation might threaten life. We are not at the edge, where matter is sparse and star formation rare. We orbit in a quiet arm of the disk, far enough from the core to avoid its hazards, close enough to benefit from the chemical enrichment that makes rocky planets possible. Our location is ordinary, but ordinariness has allowed the stability necessary for life to develop and flourish. The reflection extends to the question of life itself. The Milky Way contains hundreds of billions of stars, and we now know that most have planets. Even conservative estimates suggest billions of potentially habitable worlds scattered throughout the galaxy. Are we alone, or does the Milky Way harbour other forms of life, other intelligences, other civilizations looking up at their night skies and asking similar questions? We do not yet know, but the reflection on this possibility changes how we see the galaxy. It might be not just our home, but home to countless others, a community we have yet to discover. There is also reflection on the impermanence of all things. The Milky Way will not last forever in its current form. In 4 billion years it will collide with Andromeda, merging into a new galaxy. Over even longer timescales, star formation will eventually cease as gas is depleted. The galaxy will age, its stars dimming, its structure dissolving. Nothing is eternal. But before that far future arrives, the Milky Way will continue its dance, producing new stars, new planets, new possibilities. The reflection on impermanence is not nihilistic, but realistic, acknowledging that everything changes while also recognizing that change itself is creative. Reflection on beauty finds expression in the Milky Way's visual appearance, whether seen as a pale band across a dark sky, as a photograph revealing spiral arms and glowing nebulae, or as a computer simulation showing its three-dimensional structure. The galaxy is beautiful. This beauty is not incidental but reflects underlying order. The spiral arms follow mathematical patterns. The distribution of stars reveals gravitational dynamics. Even the colours, reds from glowing hydrogen, blues from hot young stars, yellows from older suns, encode physical information. Beauty and truth intertwine in the Milky Way, each enhancing the other. The reflection on meaning confronts the existential questions that knowledge about the galaxy raises. In a universe so large, on a planet so small, do individual lives matter? The answer depends on what you value. If mattering requires being at the centre, being unique in location, then perhaps not. But if mattering comes from consciousness, from the ability to understand and appreciate, from the connections we form with each other and with the cosmos, then yes, we matter, because we are the part of the galaxy that can reflect on itself, that can wonder and question and seek understanding. That capacity, rare as far as we know, is a form of cosmic significance. Another reflection considers the role of mystery. Despite all we have learned about the Milky Way, much remains unknown. What is dark matter? How do spiral arms form? How common is life? How did the galaxy's central black hole grow so massive? Each answer raises new questions. The reflection here is that mystery is not a problem to be eliminated, but a feature of inquiry. The Milky Way will always have secrets, and that is part of what makes it endlessly interesting. Complete knowledge would end the conversation. Ongoing mystery keeps us engaged. Finally, there is reflection on home. The word galaxy comes from the Greek for milk, but the word home comes from Old English, referring to a dwelling place, a village, a familiar location. The Milky Way is home in the deepest sense. It is where we come from, where we exist, where everything we have ever known takes place. Calling it home is not metaphorical but descriptive. We belong to the Milky Way as surely as we belong to Earth or the solar system. Understanding this belonging, feeling it not just intellectually but emotionally, is perhaps the culmination of all the reflection. The galaxy is not out there. We are in here, part of it, made of it, sustained by it. Home is not a distant destination, but where we have always been. The journey through understanding the Milky Way does not end with a single revelation or moment of completion. It continues, each generation building on what came before, adding new observations, refining old theories, discovering new mysteries. The legacy of studying our galaxy is not a finished product, but an ongoing conversation between humanity and the cosmos. A dialogue that began when the first humans looked up and wondered what that pale band of light meant. That conversation has evolved from myth to science, from simple stories to complex models, but its core motivation remains unchanged, the desire to understand where we are and what surrounds us. The legacy left by centuries of astronomers, physicists and dreamers is immense. We now know that the Milky Way is a barred spiral galaxy, roughly 100,000 light-years across, containing between 100 billion and 400 billion stars. We know it has a supermassive black hole at its centre, spiral arms traced by young stars and nebulae, a halo of ancient globular clusters, and an envelope of dark matter extending far beyond the visible disk. We know it formed over 13 billion years ago, that it has grown through mergers with smaller galaxies, and that it continues to evolve. We know our position within it, about 27,000 light-years from the centre, in a minor spur between major arms. This knowledge has practical applications. Understanding the Milky Way helps us navigate spacecraft through the solar system by providing a reference frame for celestial mechanics. It informs searches for exoplanets by showing which types of stars are most likely to host habitable worlds. It guides efforts to detect gravitational waves by predicting where compact objects might merge. It even influences technology development. as instruments designed to study the galaxy often find applications in other fields. The legacy is not purely academic, but woven into the fabric of modern science and technology. The cultural legacy is equally significant. The Milky Way appears in literature, music, art and film, serving as a symbol of vastness, mystery and home. It has shaped how we think about our place in the universe, contributing to philosophical frameworks about meaning and significance. It has inspired generations to pursue careers in science, to build telescopes, to seek answers to cosmic questions. The galaxy is part of our collective imagination, recognised even by those who have never studied astronomy in depth. But the legacy also includes humility. Every major discovery about the Milky Way has displaced humanity from centrality. We learned we are not at the galaxy's centre. We learned the galaxy is not the universe, but one among billions. We learned that most of the galaxy's mass is invisible, made of something we do not yet understand. Each revelation has required adjusting our sense of importance, recognising that we occupy no privileged position. This humility is itself a kind of wisdom, a recognition that the universe does not revolve around us, but that we are participants in something far larger. As we close this exploration, we return to where we began, the night sky. The band of the Milky Way stretches overhead, as it has for billions of years, as it will for billions more. It looks the same to your eyes as it did to the ancients who named it, to Galileo who first resolved it into stars, to Shapley who measured its scale, to Rubin who discovered its dark matter. The immediate experience has not changed. What has changed is understanding, the knowledge we bring to that experience, the context in which we see it. When you look at the Milky Way now, you see more than a pale glow. You see a galaxy, a structure of immense complexity containing hundreds of billions of suns. You see the place where you were born, not just Earth, but the larger system that made Earth possible. You see the furnaces that created the atoms in your body, the clouds where new stars are forming, the halo of dark matter binding everything together. You see time stretching backward billions of years and forward billions more. You see home. The return to simple observation, informed by knowledge, completes a cycle. We began with wonder at the night sky, moved through investigation and discovery, accumulated facts and theories, and now return to the sky with deeper appreciation. The Milky Way has not changed, but we have. We see it differently, understand it better, feel connected to it more profoundly. This cycle, from observation to understanding and back to observation, is how humans make sense of nature. It is the pattern of all science, applied here to our cosmic home. The legacy we leave to future generations is not just knowledge but questions. What will they discover about the Milky Way that we have missed? How will they refine our maps and models? What mysteries will they solve, and what new mysteries will they uncover? The conversation continues beyond us, each generation adding their voice. The Milky Way will remain a subject of study as long as humans retain curiosity, as long as we look up and wonder. There is comfort in knowing that the galaxy endures. Civilizations rise and fall, species evolve and go extinct, individuals live brief lives and pass away. But the Milky Way continues its rotation, its stars shining, its arms spiralling, its story unfolding. We are part of that story, a small part, but a real one. The atoms that make us up have been part of the galaxy for billions of years and will remain part of it long after we're gone. In that sense, we are immortal, not as individuals, but as matter, as participants in the cosmic cycle. As this exploration draws to a close, the invitation is to carry this knowledge forward. Look at the night sky when you can. Find a place dark enough to see the Milky Way clearly. Let your eyes adjust and watch as the band emerges, faint at first, then more distinct. Trace its arc across the sky. Notice the bright regions and the dark lanes. Remember that you're looking at your galaxy from inside, that every star you see belongs to this system, that you belong to it too. The Milky Way is not a distant abstraction, but your home, an understanding that changes everything. The closing is not an ending, but a return to the beginning, to the simple act of looking up. The knowledge remains, informing what you see, enriching the experience. but the experience itself is primary, direct, unmediated by telescopes or equations. The pale band of light stretches overhead, and you stand beneath it, part of the galaxy, looking at the galaxy, made of the galaxy. The circle is complete. The Milky Way is your home, and you are home within it. Good night, and sleep well among the stars.